All right, guys, it is time to start calculating t-tests. We're going to start out with the most simplistic one, the single sample t-tests. Okay, I'm going to use an example that I sort of stole from my children. They are all big fans of Minecraft. In fact, we all like Minecraft in this family, but they are particular fans of these streamed speed runs where people run from the beginning of the board or the beginning of the game all the way to beating the game in as quick a time as possible, and they compete to see who can do it the fastest. Okay, so remember that when we did z-tests, we used a 6-step process for hypothesis testing. Okay, we are going to continue with these 6 steps for hypothesis testing. I realize this might seem a little old hat, repetitive at this point, but it should mean that that basic schema you used for the z-test, you can sort of carry forward for the t-test, for each type of t-test, and you'll see we'll actually carry it forward for the ANOVA, the chi-square, and every type of hypothesis test we can use can conform to this basic 6-step process. So before we actually flesh out the steps, let's see the example and then we'll walk our way through it. So a single sample t-test. I put the formula up there. It's the same formula you saw at the end of the last lecture. It's the sample mean minus the population mean divided by this new measure of standard error that we have to get from sample standard deviation. Okay, we don't know population variability. That's why when we compare our sample to our population, we have to use a single sample t-test instead of a z-test. Right? Okay, so as I said, my family really likes Minecraft. We even have, I should have shown you pictures of this somewhere in the lecture, a survival world that is so big, I created a Christmas tree in this damn thing that's multi-stories tall that one of my kids posted to Reddit, and it got 4,200 upvotes. I know they tell me that's really cool. I just liked building the Christmas tree. So anyway, we're kind of obsessed with the game, right? And so I was talking with the kids about whether or not they thought these speedrunners, these folks that ran through the game at full speed, were they really any better than normal players? Or is it simply that they had the technology and free time to record them playing the game, and so they have a record of their performance and can be scored then as such? So they're pretty sure that these guys are way. I say guys, I should be gender neutral here because I actually don't know the gender of any of these individuals. These speedrunners, these gamers, let's say, they believe that these folks are indeed better. So what we did, and some of these data are fictitious, okay? Mojang, the publisher, the creator of Minecraft, does not actually report what the average time is for a normal player to beat the game. I'm just putting in 900 seconds as an arbitrary value here, so don't read too much into the actual generalization of these data. So it says, according to Mojang, the average time to beat the game as fast as possible for a normal player is 900 seconds. All right, that's about 15 minutes. In fact, exactly 15 minutes. We recruited the top 5 gamers from the website speedrun.com that keeps tracks of speed runs and asked them to beat the game as fast as they could. Their times are below. So the question is, do these gamers actually beat the game faster than the average player? So Illumina comes in at 833 seconds. RainX comes in at 847 seconds. Xylonox at 847 seconds, a tie there. Looks like Dave1E, Dav1E, maybe Davey, comes in at 856 seconds. And Minecravenger, the German, comes in at 860 seconds. Okay, so the question is, does this sample of gamers differ from the population? Right? We have 5 individuals. We can calculate their sample mean. We can calculate their sample standard deviation. And we can ask then whether or not those characteristics allow us to conclude whether or not these individuals are different from the larger population of normal players. So let's do it. Let's go through the 6 steps for a single sample t-test. All right, first we need to identify the populations. Well, we are comparing gamers in a Minecraft speedrun, gamers sort of being the population, versus ordinary players in a Minecraft speedrun. Okay, question is, are they really the same population? Are gamers any faster than ordinary players? Right? Are they slower even? Well, our prediction was actually directional, as we'll see at the hypothesis. What does this mean? Well, we're comparing a sample mean to a population mean to ask whether or not that sample mean is likely or unlikely, given what we know about all those possible values of the sample mean. This means we're looking at a distribution of means. Okay, the test, we know that we have information about a sample mean, information about a population mean, but we do not know population standard deviation, which means we can't run a z-test, but because we have just one sample, we can run a single sample t-test. The data are interval, right? That's times, seconds, right? It would be the variable here. Participants are selected from leaderboards, so not entirely random, but that's probably okay here because the generalization we're trying to make is that gamers are or are not different from the larger population. So we want to get those gamers. So that's not really a problem here. And as I said, for all the examples we do in class, we're going to use small sample sizes. And that's just because it takes a long time to do the example if there are large sample sizes. I've made separate videos for examples like that you can see. But again, for the lectures, we'll keep them small. So we're going to kind of bust this assumption a little bit, but we'll just pretend we've met it so we can go through with the example. All right, so you ignore that. We have central limit theorem beat just fine. Okay, so the null and research hypotheses. The null hypothesis. The top gamers on speedrun.com do not beat Minecraft any faster on average than ordinary players. Right? It says there's no effect. Our independent variable, gamer versus ordinary player, does not have an effect on our dependent variable, the time to beat the game. Our research hypothesis, right? Our sexy one, the one that we want to prove, the one we want to find support for. It says the top gamers on speedrun.com do beat Minecraft faster on average than ordinary players. Okay, so note that we are specifically saying a direction of this effect, which means we have a directional hypothesis. This will be important when we figure out what our cutoff value is later on. Okay, so the next step is to determine characteristics of the comparison distribution. Remember, this just means finding the values that plug into your t equation. You're finding out the distribution of means, what the center point is, what the mean of the distributions of means is. Well, we know that's equal to the population mean, which is given here as 900 seconds. So I don't know why it says 1200 seconds. I'll fix that now. Okay, so now that that's fixed, 900 seconds is what we're going to be working with here. We know that's based on a sample size of 5. We know that we already have the sample mean, 848.6, so we have almost everything that we need up here. What's missing? It's that S of M thing, right? That standard error. So if we look over here on the right, we can see the formula for standard error. Easy. Standard error is equal to S divided by the square root of N. Oh wait, shit, we need to get S. Remember, we just learned how to do S, though. That's just standard deviation. The only thing that differs is just before you take the square root, you divide by n minus 1, the degrees of freedom, instead of n, to account for that difference in variability of small versus large samples. Okay, so that's what we have. That's what we need to get to. Let's do it. First step is to calculate the average of the speedrun times for these gamers. Right, so we can get that to 848.6. Now, you can see with our equation for standard deviation, we need to take x, right, all these values, and subtract off the mean of x. And so we'll do that next, getting all these sort of deviation scores. Those get squared, and then we can add all of those together to get our sum of squares. Right, so no problem. Plug in some of these values here. Right, 433.2, n is 5, so n minus 1 would be 4. We can then calculate that out to a standard deviation of 1.04. Well, don't forget, we're not using standard deviation here, we're using standard error. We're not trying to find the spread of the raw scores, we're trying to find the spread of the comparison distribution, the distribution of sample means. And so we have to divide by the square root of n, so let's plug in 1.04 into the numerator of that other equation, plug in n, 5 into the denominator of that equation, and solve to get a standard error of 0.47. Okay? Now, what's the next step? Next step's easy. In fact, we're on sort of the downhill at this point. We've done all the hard work. Determine the critical values, the cutoffs. Well, in behavioral sciences, we use p equals 0.05, right? So unless I tell you otherwise, you're always going to be using p equals 0.05. Our hypothesis in this case was that the top gamers on speedrun.com do beat Minecraft faster on average than ordinary players. So because that's directional, our hypothesis test is one-tailed. So make sure you're paying attention to this sort of thing, because this is what's going to help clue you into the values that you expect to see. This then goes into the t-table, right? So this is a snippet of the t-table that I've provided to you. All 5% has to be in a single tail because this is a one-tailed test. So we go into this with their degrees of freedom of 4. We carry that into that particular row. So here it is. And we go all the way over to the column that says that we have 5% in one tail. So get used to working with your Z and T tables because they're not always the most intuitive in their structure. This gives you a T cutoff score of 2.132. Now, should we be using the positive 2.132 or the negative 2.132? Well, what we would be predicting here is that the speed run time of a gamer, right, see our prediction, is faster than the speed run time of an ordinary player. Faster in time means lower, right? And so we would expect that M would be smaller than the mu, or the population of M. Right? And so if we assume that much to be the case, then no matter what those values are, if M is lower than population, then we would expect it to result in a negative value, and we would expect it then to be on that left side of the distribution, right? Lower than 0 over there on one side. And so our T cutoff should be a negative value, a negative 2.132. Right? Something that would look a little bit like this. Because we're expecting the sample mean to be higher than the population mean, that means our t-statistic should end up being negative. If we expected our sample mean to be higher than the population mean, then we would expect our t-statistic to come out positive. Right? And so your one-tailed test has to pick the cutoff that's on the appropriate side of the distribution for what the hypothesis is predicting. Okay, so rolling downhill fast now. Let's calculate the test statistic. Nice and easy. We already know the sample mean. We already know the population mean, right? Those were given in the problem, or at least one of them was. And we calculated standard error already, so we can plug all of that in, right? 848.6 minus 900 divided by 0.47. Solve that top part first, get a negative 51.4 divided by 0.47, and we get our t-statistic. Big, right? Negative 109.36. You're not going to frequently see t-statistics quite this large, but it is still possible. It just means, realistically, that if we have our distribution, right, and our cutoff value of 2.132, at negative 2.132, our t-statistic is way the hell into the tail, right? It's way, way, way over there into the tail, which means it's basically really unlikely to have occurred due to chance alone. Well, what does that mean? Well, we can make that decision a little more firm and say we can reject that null hypothesis because a negative 109.36 is way lower than a negative 2.132. It's way further into that tail. Okay, how do we report that with respect to APA style? How do we word that? So when I ask you to make a decision, this is what I'm looking for. Something like the top gamers on speedrun.com do beat Minecraft faster on average than ordinary players. You can include the means if you'd like in parentheses. Remember to italicize that capital M. And then most importantly, at the end of your sentence, before you hit a period, put a comma, and then you need to put the results of that t-test. So we do that by a lowercase italicized t. The degrees of freedom is equal to our t value, usually just the absolute value. And then if it's beyond our cutoff, and it's not likely to be due to chance, then we say it's a p less than 0.05. If instead it was closer to the middle, it wasn't beyond our cutoff, we'd say it was a p greater than 0.05, right? So just a quick sort of rehearsal of what you're doing here. Write the symbol for the test statistic, always italicized, always lowercase. Write the degrees of freedom in parentheses. If it's a z, you just write n. Write an equal sign, then the value of the test statistic, always rounded to 2 decimal places, almost always the absolute value. Write a comma, and then whether the p-value associated with the test statistic was less than or greater than the cutoff p-value, right? Usually 0.05. If you're doing this in statistical software, you don't need to say whether it's greater or less than p was 0.05. You can actually say what the p-value is specifically. So it could be 0.02, 0.03, and then your reader can obviously make the determination that it is in fact under 0.05. Okay, if you want another example of this, I told you I've already got a packet of problems that you can work through, but here's one more. I'm not going to go through the whole thing with you right now, though. This is more of extra stuff for you to work on to make sure you understand the single sample t-test. So the citizens of several Georgia towns are worried that a fiberglass insulation plant is polluting the local environment. A doctor at one hospital, our sister of the failing Mercy, noted 3 babies born with a coccyx tailbone in the past year. Digging deeper, she read a report in Human Pathology, this is a Dow and Netsky 1984 publication, that between 1884 and 1984, only 23 babies were born with tails, right? If this is the case, she believes her hospital data to be unusual. But she also writes to doctors at 8 other hospitals to determine how often they had seen this birth defect in the past year. So, we have data from a number of different hospitals. We have a sample of data on how frequently tailbones are found in newborn babies. This is protruding tailbones, not the tailbone we all would have. And we want to compare that to a population value. So we know the population mean. It says between 1884 and 1984, only 23 babies were born with tails. So that can be reasonably thought of as a population value, having covered about a 100-year period there. The question is, how do we use that information? Well, first we know we need to calculate things about our sample, right? We need to find the average number of tails across these various hospitals. So we know our sample mean. That's easy. We've done that. Add them up, divide by the sample size. In this case, it adds to a total of 8, and there's a sample size of 8 hospitals. So, excuse me, this is 1, 2, 3, 4, 5, 6, 7, 8. It's 10 hospitals there. So it should be 8 divided by 10. You should have an average of 0.8. So I'll fix that here. So if we have that sample average, we can create sample standard deviation, right, by subtracting the mean from all of those and squaring those values and getting a sum of squares. So we can do all of that. We've already done that before. And once we know all that about the sample, we can compare that to the population, right? So what is our population value? Well, this is a 100-year period, whereas our sample is based on a 1-year period. So we need to change one of them over to another format, right? And so let's say if 23 babies were born in a 100-year period, what's the average that would be born in a 1-year period? That's easy, right? It's just 23 divided by 100. So our sample mean, our population mean, would be 0.23. Our sample mean would be the 0.8. And we could then plug in the rest of the values of our standard error calculated from sample standard deviation, and we should be able to calculate whether or not this is an unusual event or a highly likely event. So it's just like the previous example. If you want to go through this one, it'll certainly give you practice. If you want to go through the ones in the practice problems that I've also included that are not part of the homeworks or anything like that, then do that. Just make sure you've practiced this, make sure you understand this, and once you've turned in homework, make sure you read comments that I add to that homework so you can see that if you made an error, hopefully you can see where that error was made, because I try my best to explain those. Okay, so that's a single sample t-test. Next, we want to talk about paired samples t-test, and then finally the independent samples t-test. And then we'll be done. You guys can do some homework and get ready for an exam. All right, cheers.